Test 1 Exam Wrapper. Problem 4. Question. Consider a rock climber of mass 60 kilograms who is ascending a vertical wall and stops for a rest by leaning back on her rope, as seen in the diagram. The rope has some unknown tension and makes an angle of 31 degrees with the vertical. As the climber rests, the wall exerts a force, F, of unknown magnitude. This force points at an angle of 15 degrees above the horizontal, as shown in the figure. Part A. Determine the magnitude of the tension in the rope required for the mountain climber to remain stationary. Please start from a fundamental principle and show your work. The first step is to draw a force diagram. As you can see here, I had the tension force, and then I have the wall force and the gravitational force. Step 2. You recognize that since the climber is stationary, the net force on the y-axis is equal to 0. Step 3. You calculate the force on the climber due to gravity. You know the gravitational constant is equal to 9.8 meters per second, and the gravitational force is equal to that times the mass, which is 60 kilograms. Then you end up getting 588 newtons. Step 4. Notice that all the forces on the y-axis add up to 0. So then you have the tension force that you find for the y-axis, which is F sub t times cosine of 31, plus the wall force on the y-axis, which is F sub w times sine of 15, and then you subtract the gravitational force since it is pointing downwards. And that is all equal to 0. Step 5. Notice that the wall force equals the tension force times sine of 31 divided by cosine of 15, and plug that in for F sub w. Also plug in the value that we got in step 3, 588 newtons for the gravitational force. And it's still set equal to 0. You can see here that I did that. And then in step 6, you solve for the magnitude of the tension force, F sub t. So you follow all the steps and you do some algebra, and you end up getting the magnitude of the tension in the rope required for the mountain climber to remain stationary is 590.85 newtons. Part B. Determine the magnitude of the wall force required for the mountain climber to remain stationary. Please start from a fundamental principle and show your work. Step 1. Recognize that since the climber is stationary, the net force on the x-axis is equal to 0, which is similar to what we just did in Part A, but that was for the y-axis. But here the net force, F net of x, is 0. And then you notice that all the forces on the x-axis add up to 0, since it's equal, F net is equal to all the forces on the x-axis, F net of x. And for this, for the tension force for the x-axis, it's F sub t sine of 31. And then for the x-axis of the wall force, it's S sub w times cosine of 15. So we subtract that since the wall force is negative for the x-axis. And so that's equal to 0. And step 3, you recall from Part A. In step 5, that we said that the wall force was equal to the tension force times sine of 31 divided by cosine of 15. So you remember that for the wall force. And then you plug in the value that you found in Part A for the tension force, and you solve for the magnitude of the wall force. So you do some algebra, and you end up getting, for the wall force, the magnitude of the wall force required for the mountain climber to remain stationary is equal to 315.047 newtons. Part C. Calculate the minimum static coefficient of friction between the climber's shoes and the cliff required to remain motionless in the position shown. So for the first step, you need to know that the formula in order to calculate the static coefficient of friction is the force of friction is equal to mu, which is the static coefficient of friction, times the normal force. Then you need to recognize that the friction force will be at its max right before the shoes slip. For step 3, using your trig rules, recognize that the normal force is equal to the wall force times the cosine of 15. And then in step 4, using the trig rules again, recognize that the friction force is equal to the wall force times the sine of 15. So step 5, with this knowledge, plug in the values into the formula in order to calculate the static coefficient of friction, and then solve. So you do some algebra, and you notice that the wall force ends up canceling out, like in being equal to 1. And then cosine of 15 over sine of 15 is the tangent of 15. So mu equals tangent of 15, which is approximately 0.268, which is the minimum static coefficient of friction between the climber's shoes and the cliff required to remain motionless in the position shown. So as a recap, these are the solutions for part A, B, and C for problem 4. 590.85 newtons per part A, 315.047 newtons per part B, and 0.268 for part C. And that's the end of problem 4. Thank you.